Okay, this is Web of Science 6F, problem number 17, video 3-3. A space station is constructed in the shape of a hollow ring of mass 4.1 times 10 to the 4th kilograms. Members of the crew walk on a deck formed by the inner surface of the outer cylindrical wall of the ring with radius 100 plane meters. At rest, when constructed, the ring is set rotating about its axis so that the people inside experience an effective free fall acceleration equal to g. Sphere below, the rotation is achieved by firing two small rockets attached tangentially to opposite points on the rim of the ring. What angular momentum? That is the space station. Okay. So, part A. Part A needs angular momentum. Angular momentum is equal to IW. So that's moment of inertia times the angular velocity. And if you look at this, we have no speed. We have a mass, and we have a radius. We have zero units for speed or any sort of velocity, but we do have this free fall acceleration equal to g. And it's spinning, right? The thrusters are the thrusters, is that what it's called? Two small rockets, okay, whatever. The rockets are going to cause this spin to occur. The y is known as a centripetal acceleration. Yeah, okay, centripetal acceleration. Okay, so that's how we're going to use the centripetal acceleration to find this. V value, because as we know, this is. Let me just write that down. So moment of inertia of a rotating cylinder is mr squared. It's just what we know, so mr squared times r v squared over r. No. Yeah, times w over r. Okay. So what we're going to do here is using the centripetal acceleration, which is, this is velocity squared over r. This is then equal to rw squared. Now, the reason it's rw squared is because if you cancel the units, we got r, v squared, r squared. These cancel, so you got v squared over r. So that's what this r, just rw squared comes into place. Then all of a sudden we have AC is equal to R, sorry about that, not W, I keep saying W, it's just a habit. I don't remember the Greek name of it, so we're just going to call it, it's angular velocity, is what we call it. Angular velocity is alpha? Is it omega? Maybe. No, it's not omega. Never mind, okay. Angular velocity. So then we got AC equals R, and we need this W value. We need this W value right here, because that's what we need to plug into here. So we got W squared is equal to R, W is equal to, let's see where, but we do not keep it as AC. You want to know why? Because this free fall acceleration is equal to G, so that's what we're going to call it. And G, as we know, is equal to 9.8 newtons times kilogram, or yeah, newtons over kilograms, or meters per second. So all of a sudden, this equation, let me use a different color here so we can differentiate. All of a sudden, this equation will become, can I zoom in? There you go. L is equal to mr squared times this gravity over radius, right? And to go even further, we can go mr, okay, mr times rgr. And from here, we just plug in our values. So, okay, so we got 4.1 times 10 to the 4th. This is kilograms. Kilograms is the mass of our hollow ring. Yeah, kilograms, okay. times the radius of this hollow ring, which is 120 meters, and then times root of the g value, which has always been 9.8. We'll do meters per second, multiplied by, again, the radius of the cylinder. So our momentum is 1.68 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. And as you can see, that's fairly close. It's correct answer is 1.69. If you round up, it is 1.69. So I'm actually gonna put that here because it's 1.687, and yeah, 1.69. So we get this answer. Now, what time interval must the rocket be fired if each exerts a force on 30 minutes? Okay. So now we got to utilize a cross product. Well, here, let me explain real quick. Okay. Torque is equal to R cross F, right? Yeah. Since there's only one, there's only like one unit each. We're only going this way. We're not going this way and this way. I hope that makes sense, because you know what I mean? Okay, so this can automatically, T total, this can automatically go to R times F. But we have two rockets, so it's actually 2 RF. Radius times force, that's what the F and the R stand for. So our total torque is actually going to be equal to, that's what's asking for the correct torque. It's asking time, okay. Let me explain what I'm doing right now. So I'm finding this torque to then, hold up, I just lost my train of thought. This is the total torque being applied. So we got 2, our radius, times this new force, which is 130 newtons, or 130 newtons. Okay. Yeah, I got it. Okay, perfect. All right. From here, torque is going to be equal to, torque is equal to our moment of inertia times our angular acceleration. Done. Now, we know our torque, and we know our moment of inertia. So what we're going to do is actually set, we know moment of inertia, we just solve moment of inertia, it's right here. And then we know our torque, which is right here, and we're just going to plug that in here, and our moment of inertia, so our angular acceleration is going to be 0.00053. I believe that is it radian? Radians per square. I believe it's radians per square. Okay. We got that now. Alright, and now using this is where we plug into a kinematic. So, okay, our kinematic is going to be fancy T. Okay, our final angular velocity is going to be equal to our initial plus our angular acceleration times time. Now, this comes out to 0. So, our final is going to be equal to this acceleration times time. And we're looking for time, so our time is equal to our final over an acceleration. So then this time is going to be our final, which is, if we go back to part A, this. It's our G value over our R value. What? Yeah. Okay, sorry about that. It's not this. It's this. Yes, because we simplified to get here. Yeah, okay. Perfect. Over our this value. I'll write it out again. 1, 2, 3, 4, 5, 3. And then G is gravity again. Radius is just the radius, which is 120. So our time should come out to be 5391.96 seconds. Okay. Here's what we did. For part A, for part B, we need to find time. Now, rotational kinematics are similar to linear kinematics. It's just that we swap our velocity for angular velocity, or acceleration for angular acceleration, or time. Just looks cooler in cursive. Okay, we needed time. We needed values to plug in to find this time. So we needed to find our angular acceleration. Now, given that we could find a torque, which we did here, this is the equation we used. We knew moment of inertia. We now knew torque, so we could find this angular acceleration that we could use to find the time. Now, this final velocity is the velocity found in part A, utilizing our momentum formula, utilizing this centripetal acceleration hodgepodge, which then spat out that, which was our W, which is why this W is equal to this W. And then you divide it by our acceleration, because that's what because time would be equal to the angular velocity divided by the angular acceleration. Big mistakes that can be made here. Initially, our first step was our huge mistake. This right here, that took me forever. Did not have common sense to understand. Well, I wouldn't say common sense. I guess you need kind of some into. That's not what I want. We're going this way. We're going this way. So our centripetal. Boop. Boop. We're feeling that force that way. Got it? Yes. We need to utilize this G value to plug it in here. It's a big thing, obviously. Your centripetal needs to equal your velocity squared over your radius, because that's what centripetal is. Then you gotta reason to the point that your radius times angular velocity squared is going to give you like how do I say that? Something proportional, two units together proportional to centripetal acceleration. Putting them together, swapping the centripetal acceleration for the G value to find this W. That is the hardest part about this. After that, all you do is find momentum, utilize torque into your torque equation for T equals moment inertia times angular acceleration. This is a big problem. Two parts, it might look like one of the easier ones, but if you cannot figure out how to find your initial, this right here, then it's gonna be a rough day.